So this week we're going to start in the synthesis section of the organic unit. It's the longest section in this unit, and it may take us at least 3 weeks to get through this section. We concentrate on functional groups, different types of compounds in this synthesis part, and we think about how they react to form different compounds. We're going to look in quite a bit of detail and how what actually happens during chemical reactions. So that first part there, you've already done. We've already looked at skeletal structures, and we're going to use them a lot. We're going to look at different types of organic synthesis. Remember, synthesis meaning to build something up, to make more of something. We'll look at various different reactions that you'll need to become familiar with. We're going to look at this idea of synthetic routes, so the routes to a final product, how we actually get from a reactant to our product, how the electrons move and between atoms during a chemical reaction. So all chemical reactions involve the breaking and making of bonds, breaking being an endothermic process, making being an exothermic process, but we've only really concentrated in this so far in terms of thermodynamics and energy changes during a reaction and how likely they are to happen. So we're going to move that on and look in a lot more detail at the mechanism of a reaction and what actually happens along the way as we start our reactant and form our product. We're going to look at how electrons move between atoms and how this works together. So just to start with the very basics of organic synthesis this week. So we're going to look at different types of bond breaking. We're going to look at homolytic fission and heterolytic fission. We're going to look at electrons moving and how we represent that when we're drawing reaction mechanisms. And we're going to look at different reactive species. These species are called nucleophiles and electrophiles, and look at how they initiate reactions. Right, so let's first look at the breaking of bonds, also known as bond fission. This word fission you will have come across before when you looked at the nuclear chemistry in that 5. And if you do physics as well, you'll be fairly familiar with that. So the word fission means to split apart. Okay, so bond fission meaning just to break a bond, to split apart a bond. And a bond can break in 2 different ways. It can break via homolytic fission or heterolytic fission. Homolytic fission, indicating this kind of prefix homo, indicating the same, and hetero, indicating different. Okay, and we'll look at each of them in a wee bit of detail now. So homolytic fission. You will have seen this before, although not maybe necessarily heard the term homolytic fission. You will have seen it in higher when you looked at the free radical stuff in Unit 2. I would suggest maybe having a wee quick look over that. You can use your notes if you have them, or you could go on Scholar or BBC Bitesize or something, have a wee look over free radicals. But homolytic fission is what happens during the initiation phase of a free radical reaction. We call it homolytic fission because each atom gets the same number of electrons, be it 1 electron. Each atom gets 1 electron. So here you have a bond between this X and Y. Remember, a covalent bond made up of 2 electrons. During homolytic fission, each atom takes on 1 of those electrons. So they have the same number of electrons after, or they have gained the same number of electrons after that fission process has taken place. So it results in the formation of a free radical. They're really, really reactive, they're really unstable and can be quite unpredictable. So when we're using them in organic synthesis, actually it's quite difficult to use them in organic synthesis, because when we are synthesizing something, we're doing it for a reason. We're doing it because we need it. I mean, you're synthesizing something, you need to do that in the most efficient way possible. So using a free radical when might not be in complete control over what product you're going to form is not always terribly useful. More commonly used in organic synthesis is this heterolytic fission, which means the bond breaks unevenly and one atom in the bond, so we still have our X and Y here, takes both of the electrons. So hetero meaning that each atom in the bond takes a different number of electrons. So when this splits apart, both the electrons involved in the covalent bond will jump onto the Y atom, making it negatively charged and leaving the X atom positively charged. And when we're using heterolytic fission, it is much more easy to control the products and therefore control the reactions that are happening. Right, so we're going to have a look at curly arrows. Now, curly arrows are an organic chemist's best friend, and we use them to show electron movement during reactions. There are two different types. You have a single-headed arrow that you see here, and you'll see that it's like a wee half head on an arrow, and it denotes one electron moving. So the starting point here is where the electron is to begin with, and the arrowhead shows us its destination, so where it ends up, where it moves to. A double-headed arrow, which is the one we'll use much more commonly. Again, the start is the source of the electron, and the arrowhead shows us where it is going, and it denotes the movement of an electron pair, not just a single electron. Okay, so some examples. Here is a homolytic fission, and we use two single-headed arrows to show that one electron is moving on to this hydrogen, and what the other electron from the bond is moving on to this hydrogen to give us our free radicals. Again, a wee reminder, I would go and just have a wee refresher look at that. So in this homolytic fission, using these single-headed arrows, we have an electron pair dissociating, breaking apart to give one electron on each hydrogen atom. Now our double-headed arrow shows both the electrons that are contained within that covalent bond, both moving to one of the hydrogens. So because the electron pair has moved here, we get one positively charged ion and one negatively charged ions. And when you are denoting electron movement using the double-headed arrow, you do often form an ion. What I want you to pay really close attention to when you're drawing arrows, and you will have to know how to draw them properly, is that the start of the arrow must begin where the source of the electron, and the head of the arrow is where it ends up. So just a quick example. This is just a type of nucleophilic attack. We're going to look at that in a bit more detail in a minute. Here we have, and this is called a nucleophile, and that is it's an electron-rich substance. So here is our source of electrons. They're moving from the nucleophile and attacking this carbon here. As that happens, a pair of electrons from the double bond moves up onto this oxygen. Have a look at what happens between here and here. Our nucleophile attacks here, and as it does that, this pair of electrons has formed a bond between the carbon atom and the nucleophile. Once that has happened, we have a negative charge on our oxygen. An electron pair moves between the oxygen to the hydrogen, forming a bond over here. Let's have a think now about what we need in order for reactions to happen. We need some sort of reactive species, and the first example we're going to look at, one that you're going to be looking at a lot, is a nucleophile. A nucleophile is an electron donating species, which means it has spare pairs of electrons. It's quite electron rich. And examples are about any negatively charged ion, you have a list there, and then some neutral molecules like water or ammonia, which have some lone pairs on them as well. So if we just take a wee note that, I have lone pairs, which I've just drawn in as well. They will seek out electron deficient sites, noted by this, remember this slightly positive end of molecules that we spoke about a lot in higher. They will seek out those areas on a molecule and they will attack. And we're going to use that phrase a lot as well. So I'll go through very quickly a kind of general example of a nucleophilic attack, and then we'll look at more specific examples the further we get through this topic. In order for a nucleophile to attack, we need to have a slightly negative part of a molecule. So if you think about this carbonyl bond, okay, carbon has an electron negativity of 2.5. Oxygen has an electron negativity of 3.5. So that would make this end of the molecule slightly positive, this end of the molecule slightly negative. Remember, the electron negativity means that the shared pairs in that bond are going to get pulled towards the oxygen, which means in reality, in this molecule here, this end's going to be slightly positive, this end's slightly negative. So when you then have your nucleophile, it will attack that slightly negative end, and as a result, one of the pairs of electrons, it will be the electrons that form the pi bond in this case, jump on to the oxygen. This is quite often done under acidic conditions, so you're going to have a little hydride ion, a hydrogen ion. That oxygen has taken on the negative charge from this pair of electrons jumping up here, and it seeks to form a bond with something, and we have that hydrogen ion there which it will form a bond with. So let's look at the bond breaking and the bond forming. You have a nucleophile attacking here, and as we move from the structure we start with to our intermediate of sorts here, a bond is formed. So it forms a bond between the nucleophile and the carbon atom. Okay, and we see that here. We then, our negative charge, which has come on purely onto the oxygen, this arrow starts at the oxygen and comes round to the space in between that oxygen and that hydrogen, denoting the formation of this bond here. Okay. So the second reactive species we're going to look at are electrophiles. We can think of them as the opposite of nucleophiles, where nucleophiles are electron rich, electrophiles are electron deficient. and they are seeking out electrons because they love electrons. Just as a wee reminder, they are quite often positively charged ions, so something like a hydrogen ion, or an electron deficient molecule like sulfur trioxide there, and they are seeking out a part in a molecule or an atom that has a negative charge. So a little example here. We have, this is an electrophilic addition. Now this is just a common addition reaction that you would have looked at in National 5 that we're just going to look at in a wee bit more detail. So we have this is an ethene molecule. We have our carbon to carbon double bond, which is electron rich. And we have a hydrogen bromide molecule here. Hydrogen with an electron negativity of 2.2, bromine an electron negativity of 2.8, making this end slightly positive and this end slightly negative. So if I apply that in here, just so you can see it, this electron rich site, so basically our pi bond attacks this hydrogen here, and the pi bond breaks and forms a bond between this carbon and this hydrogen. As that happens, the pair of electrons holding the hydrogen and the bromine together break and jump onto the bromine forming a bromide ion. So here we have this bond which is formed here, and then we have our bromide ion being attracted to this carbon here. Now this intermediate is called a carbocation. That's what's being produced. It's a carbon-centred positive ion. The negative bromide ion is attracted to that. This arrow here representing the bond forming, and there is our final molecule. So those are the basics of organic synthesis. So looking at the curly arrows, what is a nucleophile? What is an electrophile? We're now going to spend the rest of this topic, which as I said will take a few weeks, looking at different classes of compounds and the different reactions that they show. Right, so on the screen now is just the names of those molecules. You can have a wee look over them, just pause it and have a wee look. If this is something you're not terribly comfortable with, you can send me a wee email and we can go over it, or you can come to a drop-in session and we'll go over it, and I can send you some exercises if you want a little bit of extra practice on this as well. But let's move on to classifying. Now, when I'm talking about classifying, I'm talking about classifying in a similar way to you would classify alcohols. So if you remember it higher, you had to know how to classify an alcohol as primary, secondary, or tertiary based on how many hydrogens were attached to the carbon atom that the hydroxyl group was attached to. It is the exact same for classifying monohaloalkane. A monohaloalkane will contain only one halogen atom. So if we look at this one, if you have two hydrogens, if this X represents our halogen, if you have two hydrogen atoms on the carbon, then it is primary, and we can notify that, we can show that by just drawing that. If it is on the carbon with only one hydrogen, it is secondary, and if it is on the carbon and it has no hydrogens directly bonded to it, then it is tertiary. So let's have a wee look at these. We'll just talk through these together. Here we have a monohaloalkane. There is our halogen atom there. If we look at the carbon that it's bonded to, it is only directly bonded to one hydrogen. So it's only bonded to one hydrogen. Therefore, it is secondary. That's not a 1, it should be a 2. It's secondary. This one here, there is our halogen, and the carbon it's bonded to is not directly bonded to any hydrogens. Therefore, it is tertiary. If we have a look at this one, There's our halogen. The carbon it's bonded to has 2 hydrogens directly attached to it. So it is primary. And this one here, there it is there in the middle. It's bonded to this carbon here, which has 1 hydrogen directly bonded to it. So it is going to be secondary. Now the next few slides we're going to look at some reactions of monohaloalkanes, and they undergo 2 main types of reaction. An elimination reaction in which a hydrogen halide molecule, so something like hydrogen chloride, hydrogen bromide, is eliminated during a reaction with a strong base. We're also going to look at a substitution reaction where the halogen atom in the monohaloalkane is replaced by whichever nucleophile is being used. So let's start by looking at an elimination reaction involving a monohaloalkane. The word elimination obviously indicating that something is going to be eliminated. We're going to lose something from the molecule that we start with, and the chances are that is going to be the halogen atom. Let's think about polarity through this molecule first of all to try and understand why the reaction starts. So if you look at the electron negativities, you'll see that you're going to end up with a wee system that looks a bit like that. That is creating an environment that this nucleophile, the hydroxide ion here, is going to attack. Okay, and that is indeed what it does. This is extremely electron negative. It's got a lot of negative charge there. The oxygen itself has 2 lone pairs, as we know, but because it has this extra pair, so it's got an overall negative charge. This is provided by the base that the reaction happens in, and it attacks in here and forms a bond between that oxygen and the hydrogen. That hydrogen is quite happy to go away there. So the pair of electrons in that bond jump onto that carbon. So we're eliminating, first of all, a hydrogen as it's attached to a water molecule. So we have our carbon here with this negative charge. It jumps in here and forms a double bond. And the pairon in this bond jump onto the chlorine atom, and it is eliminated. It eliminates a Cl atom, forms a, what am I doing? That's not how you spell atom. It forms a chloride ion. Okay, so let's just go through where these arrows here. So we have a lone pair of electrons on this carbon atom. They move into between these 2 carbon atoms and make that single bond now a double bond. When that happens, the pair of electrons that make this bond move onto the chlorine atom, forming the chloride ion. So the pi bond forms, and this is what we're left up with. Remember, we start with something that has 7 sigma bonds at the start, and we've ended up with something with 5 sigma bonds and 1 pi bond. Now, all of this happens in quite a sequential way, and it all happens, kind of all happens together quite nicely. So just to summarise that whole thing, we form a bond here, then go on to there, eliminating a water molecule. This pair jumps in here, forming the double bond and eliminating the chloride ion. And we've gone from having a monohaloalkane to having an alkene. So we're going to look now at a series of different substitution reactions involving monohaloalkanes. They're nucleophilic substitution reactions. And in these type of reactions, your halogen atom in your alkane is going to be substituted with another atom, or indeed group of atoms, or functional group. These are reactions we can control based on what nucleophile we use. So if we use a hydroxide group as our nucleophile, we're going to produce an alcohol. It gives us a lot of control. These reactions give us a lot of control over what our products will be, and hopefully you're going to start getting a sense of reaction design and how we can design different organic synthesis. So a monohaloalkane to an alcohol. We react our monohaloalkane. We've got here 1-chloropropane. We react it with an aqueous alkali like sodium hydroxide under reflux. So just a wee note to remember from your researching unit. So under reflux, we are evaporating our reaction mixture and condensing it at the same time. Okay, so we fit our round bottom flask with a condenser. We heat up our reaction mixture till we're forming gases. They're coming up, they're condensing back down. Okay, so in these reactions, the nucleophile of choice is a hydroxide group. So if we look, we've got our polarity here, and there we have our nucleophile. It's going to be attracted to this kind of positive part of the molecule, so it is going to attack in there. And as that happens, a bond is forming between that carbon and the hydroxyl group. This bond, the pair in that bond jump onto the chlorine, forming a chloride ion. So that would be like a byproduct. It would probably be mopped up with something else in the reaction mixture, like probably the sodium would form something like sodium chloride. And there is our alcohol. So we have our nucleophile attacking that positive site, forming a bond between the oxygen and the carbon. The pair of electrons in this carbon to chlorine bond jumping onto the chlorine and eliminating a chloride ion. The next reaction we're going to look at is the formation of an ether from a monohaloalkane. Ether are a group of compounds that we'll look at in a bit more detail perhaps next week. We're going to react them with something called an alcoholic alkoxide, which again we'll look at in more detail next week. We produce this by simply adding an alkoxide like potassium methoxide to methanol. And these reactions, the nucleophile that we generate here is this one here. Okay, this is an ether. We have an interrupted carbon chain here with an oxygen in the middle. That is the ether functional group, and they're really useful organic solvents. But again, it's a really simple reaction. It's really similar to the last one that we looked at. We've got our positive site here that is attacked by our nucleophile. So we're forming a bond between that oxygen and that carbon with a lone pair jumping onto our bonding pair jumping onto our chlorine. We're eliminating a chloride ion, which will get mopped up with something in the mixture, and we're forming our ether. So this part of the molecule here, I just want to try and highlight to you as best I can with my dodgy drawing where it all comes from. This OCH3 is this nucleophile. Okay, so that's where that comes from. So let's have a wee look at how we form a carboxylic acid from a monohaloalkane. We react it with a reagent called ethanolic cyanide. There is a cyanide ion that behaves as the nucleophile in these reactions. This is a two-step process. A little point to note that this reaction will increase your overall carbon chain length by 1. So if you wanted, for example, to synthesize butanoic acid, you would have to start with some sort of monohalopropane molecule, okay, like we've got here. So this just starts in the same way as all the other reactions. We have our positive site that is attacked by our nucleophile. So the lone pair from the nucleophile forming a bond between the carbon of the nucleophile and the carbon in our alkane molecule here. And then that pair from the bond jumps up onto the chlorine, forming or eliminating our chloride ion. We can then convert the nitrile. Now the nitrile is a group that is formed that contains a carbon to nitrogen triple bond. Okay, so this bit here is our nitrile. It can then be converted to the corresponding carboxylic acid by something called acid hydrolysis. It is quite a complicated reaction mechanism. I'm going to actually talk through it on the next slide, but I just want to point out that it's quite complicated. It's not something that you need to know. You don't even need to watch it if you wouldn't like to. But for those of you who are interested, and I know there's probably a couple of you are, I'm going to talk through how we get from this nitrile group that we see here, our carbon to nitrogen with a triple bond, to our carboxylic acid group. So this is acid hydrolysis, so it's done under acidic conditions. So we contain our hydronium ion, and there it's there. Our nitrogen is quite electronegative. We've got a lone pair on it, so it attacks the positive site in here. And our pair from the bond here jump onto the water molecule. We eliminate, here we have our water molecule here. We've formed a bond between this hydrogen and this nitrogen. Our nitrogen now has quite a positive, has a kind of positive charge to it. Our water is quite reactive. It can behave as a nucleophile. It can react. It attacks the carbon in our triple bond there. And one of the pi bonds, the electrons that make up that pi bond, jump onto our nitrogen. And we've now got something that looks like this. It goes through a process known as tautomerization, where the electron just transfers between the electron and the electrons transfer, the protons as well, transfer between the molecules. So we get a situation that looks like this. Another water molecule will come in here and attack at that point there, with a pair jumping up onto that oxygen. So we've now got this. It goes through another proton transfer process where one of the hydrogen atoms from this group here will jump onto our amine group, forming this. At that point, a lone pair from here will jump on there and eliminate that ammonia molecule there. And if you follow the bonds, we've now formed a carbon to oxygen double bond, but it's still attached to that hydrogen. This hydroxide here is now here. There's our R group. We've eliminated this. It's going to form a bond with that hydrogen. And that's going to jump on there. And we form our carboxylic acid. So you can pause that, have a wee look at it. If you're interested, have a look at, follow the arrows, look at where they start, look at where they end up. Why might that happen? But if you're not that interested, just leave it. I want to finish this week by just looking at classifying substitution reactions. They can occur in one of two ways. They can occur via an SN1 mechanism or an SN2 mechanism. And we'll talk through each of these individually. So in SN1, S just standing for substitution, N, so nucleophilic, so it's a nucleophilic substitution reaction. The 1 means that there is one molecule involved in the rate determining step. There's a link here with the kinetics section in that SN1 reactions, because there's one molecule involved in the rate determining step, are first order. And SN2 reactions, there's 2 molecules involved in the rate determining step, and they tend to be second order. So an SN1 reaction happens in 2 steps. There's a slow step, the rate determining step, and that is followed by a fast step. And tertiary haloalkanes tend to react by SN1 reactions, and we'll look at why that is. Tertiary atom monohaloalkanes, if you think about it, are quite busy molecules. Okay, if we look at the example down here, these R groups could be anything. They could be methyl, ethyl, propyl groups. They're quite busy. That whole area is busy, so there's not a lot of space for a nucleophile to come in and react directly. Okay, so this is the rate determining step. It's quite slow, and it starts with heterolytic fission of this carbon to bromine bond. There'll be something there to catalyze that reaction, but what happens is the bonding pair of electrons, the bond breaks and they jump on to the bromine, forming the bromide ion. The arrangement, the shape of the molecule is quite important here. We go from a tetrahedral shape to having a trigonoplanar, and this is an intermediate. We would classify this intermediate as a carbocation intermediate. A carbocation means a carbon-centered positive ion. So that is the first step, the heterolytic fission of this carbon to bromine bond. As soon as that step happens, the second step, which is the nucleophilic attack, happens really quite quickly. You have your chosen nucleophile and it forms a bond with your carbon in the centre there quite quickly. So we're going from having this trigonoplanar shape back to our tetrahedral shape, and we've substituted the halogen for our nucleophile. So remember, it's a first order reaction because there's one molecule involved in the rate determining step. And the overall rate of this reaction will be determined by how quickly that carbon to halogen bond breaks. This step is much more quick and happens as soon as that bond is broken. And SN2 reactions only happen by one step, and we do not this time form a carbocation intermediate. There is a transition state formed instead. A transition state is, we don't classify it as an intermediate because it's sort of halfway between your reactants and your products. Your bond that you're breaking is still kind of half formed, and the bond that you're forming is half formed at the same time. That will make a wee bit more sense when we look at the diagram in the next slide. Primary haloalkanes tend to react by that mechanism because there's more space. There's more space to have your transition state than simply your carbocation intermediate. So let's have a look at it. We've got a tetrahedral shape to start with. This is a primary. See how we've got much more space. Those R groups will be quite big. We've got much more space around the carbon for our nucleophile to attack the carbon there. Now, that attack happens at the same time as this bond is breaking, and it forms this transition state. And our transition state is trigonobipyramidal, so I would make sure we remember that. So have a look at it. We've half formed our bond and half broken that bond, and because we're a primary haloalkane, there's much more space for that to happen as opposed to an SN1 reaction where there might not be enough space, so it has to form the carbocation intermediate. The reaction proceeds. At that point there, it can go back to forming, to just having your reactant, or it pushes on, reaches your activation energy and keeps going. So it's said to show second order kinetics because we have our nucleophile and our reactant, our haloalkane, both involved in the rate determining step. So a quick summary of SN1 and SN2 reactions before I look at a couple of example questions with you. In an SN1 reaction, there is one species in the rate determining step. It's said to be first order. It occurs in a minimum of 2 steps, the first of which is our rate determining step, the heterolytic fission of our carbon to halogen bond. And it goes via a trigonal planar carbocation intermediate, and it takes place primarily where tertiary haloalkanes are involved, and that's because there's less space, it can't form that transition state. SN2 reactions, there's two species involved in the rate determining step, so it's said to be second order. It occurs in a single step via a 5-centred trigonal bipyramidal transition state. Remember, the bond you're breaking and the bond you're forming are sort of halfway there while that transition state has formed, and we see that where a primary haloalkane is involved. So you would be expected to be able to draw out the mechanisms for SN1 and SN2 reactions, identifying using the starter molecule which mechanism it will react via. So let's have a look at this one. Show the mechanism for the reaction between 2-bromomethylpropane and the nucleophile. It's a hydroxide group. So let's look first of all at our haloalkane. It is a tertiary haloalkane. So I'm just going to write all this down, keep myself right, refer back to the notes in the previous slide. So what is going to react via an SN1 mechanism, which means I'm going to go via a trigonal planar carbocation intermediate. So write all that down, just keep yourself right. There's no harm in that at all. So it starts with this heterolytic fission of my carbon to bromine bond. So the bonding pair jump on to the bromine and it is essentially eliminated. There'll be something there to mop that up. And I'll form, so this is this bond here. Nothing's happened to that, it's still there. I'll now join this bond and I'm going to draw this bond here, and the carbon in the centre has a positive charge now. Just remember that is trigonal planar. It's a trigonal planar intermediate. At that point, my nucleophile is ready to react and it forms a bond directly with a carbon in the middle. So I'm going to draw what I've got. I've still got that methyl group up there. I've still got the methyl group over here, one down here, and there is the bond that the carbon has formed with the nucleophile, forming an alcohol. And the next one, show the mechanism for the reaction between bromoethane and the nucleophile. I'll just start by doing the same thing. Look at this molecule, there's 2 hydrogens attached to the carbon, so it's a primary haloalkane. It will therefore react via an SN2 mechanism, so that is going to be through a transition state. Rather than your carbocation intermediate. So we start with our nucleophile and it attacks there, and we form our transition state. So if you just pay attention, here we have this carbon to hydrogen up here, a carbon to hydrogen down here, our carbon to methyl group down here. And at that point, as soon as that attack happens, the carbon to bromine begins to break as the carbon to hydroxide group begins to form. Now, that is in fact, that transition state is an ion. So we have to draw that in square brackets and show the negative charge on it. Okay, remember it is trigonal, bipyramidal. You need to try and remember the shapes of these intermediates and transition states. This bond then fully breaks, forming our alcohol. There you go. Right. So that, you'll be glad to hear, is all for this week. I realise that is quite a wee bit more than we've maybe had to do in previous weeks, but finding the best place to stop is a bit trickier with this, so this is what I've gone with. You've got revision questions to do. Again, please send me emails, come to drop-in sessions, anything I can do to help. Just let me know. Good luck.